Okay, this is the Monday after spring break week, and it seems like it's been such a long time, or not. I was here every day last week doing something, so I definitely know that I didn't have a break. But I did have some time off. A few hours here and there is the way I did it. This is the histogram of what the exam scores are, and the way the histogram works is it rounds up, so the fact that it looks like there's 3 people that got 92, I can't remember whether it was exactly 92. It might have been 91 and 92, but that gives you an idea of how everybody falls into a bin. So the average is 80.6. It is a somewhat strange looking distribution because it has a large mass up near the high end, and it has kind of a middle mass. Let's see, how do you want to say this? Has kind of a middle group of people in there, and then it has a tailing off down to the lower end. One of the things that I promised that I would be able to do today, and you can come see me after class or make an appointment to see me before Friday, because Friday's the last day to drop, is that everybody could have all the information with regards to grades and preliminary estimates and things like that right now. Letter grades, I can't draw an exact angle on that. If I could, I'd short circuit a month's worth of the semester, which that's going to pass soon enough anyway, right? I don't know if you're like me, but when we hit after spring break, these last few weeks are going to go by so fast that hold on, because it's going to go by fast is all I can say. So this is the distribution for the midterm. I'm basically happy. There's little things that I would like to have seen done better, and obviously if you got a score that's in the 50s, you're not happy at all, I'm sure. What can we do about that? You can come in and talk to me and see what your prospects are, and and look at the grade sheets that I have to see what your overall rating is. This exam is like 15% of the grade, so it's not the entire course. Other information that I pulled together, I refined the homework histogram that I had up. That modified slightly by adding in one more assignment sheet. And these are all on the answer key page, so I'm not really going to dwell on these. I have updated the quiz distribution, and I will be dropping the lowest quiz, so this will shift to the right slightly as a result of doing that at some point. I got inputs from the lab instructor in terms of the latest labs that he had graded. So this is that distribution. I pull all of that together and come up with what's now called the pre-final average. So this includes the preliminary estimate for the homework, the preliminary estimate for the quiz, the exact value for the midterm, and then the preliminary estimate for the labs. And it leaves out the final project, which will be a team project, which will be getting introduced in the next couple of weeks. And it leaves out the final. So basically it's a normalization based on those components missing. And what we have to look at this point is, if it was an ideal situation where I could say, you know, grading would be on a straight scale, there would be a line drawn right down in here, and I'd form my A, B's, and C's out of that. But as it stands right now, I'd probably, if this was the way the final distribution looked to me, I'd have to go inside and study a little bit about what's going on in here and decide, are those going to be C minuses? Are some of those going to be C's? And what's going to be a D and what might be less than a D? I mean, that's about all I can say right now. But if you're in that category and you feel like you need to talk to me, I definitely would plan on doing that sometime this week. I wouldn't wait till lab time on Friday, because if you need to make an important decision, you're going to want to do that probably before lab time on Friday. And just to give you a heads up, Friday is Mountain Lion Research Day for the campus, and I have posters there in the morning, so I won't really be around too much in the morning. I'll be doing my class in the morning, but I'll also be down in the whatever that old gym center is called. So waiting till Friday morning to come talk to me is probably not a good idea either. Just make an appointment to try to come in and see me sometime before Friday. Obviously, I'll meet with some people after class today too, if that's how you want to do it. Right now, the way it looks, if you were to look at this stack up in here, you'd say, so you're going to give out, I'm going to give out that many A's or A minuses. You know, if it stayed that way, that's what I'd be doing. There'd be A's and A minuses taken out of that grouping right in there. Some of those 90 scores are probably 89s, though, too. I really don't know, unless I look at my spreadsheet. The fact that there's a large hole between this area and here says that I probably have to examine how I draw the lines to have some fair number of C's and B's in there. So that probably would say that I would be going below 70. But again, this distribution is not the final one. And what I always see happen, unless this semester is bizarre like I've never seen before, is there's always a tendency for things to shift to the right as time goes on. And that says that most of you tend to do better on things near the end, or at least not drop off. Now, if you quit working, then you'll be one of those sticks that moves to the left, but most everybody tends to move further to the right as time goes on. Some of you are smiling, and that makes me think maybe an animation would be nice, right, to see how it animates over time. Never done that before, but would that be interesting or not? The life of a student in a course over time, how it animates. Some move up, some move down, some stay the same. A new video to watch when you're really, really bored. Does anybody have any questions about these histograms? What I can do for you, though, and what I usually do when somebody wants to come in and talk, is we'll put these numbers down, I'll have them on the spreadsheet, and then we'll hypothesize. And if you don't want to come in and talk to me, but just want to hypothesize on your own, you can take and calculate your own numbers, get the numbers from me, and then start hypothesizing. What if I get this on the final? What if I shift my homework average and quiz average and get this on the final project? How does that play out in the long run when you average everything up? That's the type of thing that I'll do for anybody that wants to come in and talk, is just sit down and say, how do you think you can do? Be realistic, be optimistic, kind of come up with a couple different scenarios, and then see how it looks on paper. Amazing things happen for some people. Some people have bad days, so we can't say with certainty what would happen on the final. But I am amazed at that some people just, can do really, really well on the final. And that's something that I guess I wouldn't count on, but I would take it as a nice surprise if that were to happen at the end. Okay, let's go back up to the top. I don't think I'll dwell in great detail on every page in here, but I'll make a few comments on some of the things as we go through. The complex number problems were, let's see, I've got a little analysis sheet actually, something that I have to do for assessment. you might be surprised that we do things like this, but it's one of my approaches. So I categorize every type of problem into a different type, and then I went through everybody's exam, and I took all your data and input into this big matrix, and then I run it down vertically and have at the bottom what were the percentages on each of the problem types in terms of performance, because like I said, I have to write an assessment report at the end of the semester to show how on key areas we're doing. So the average, after you average down and then you average across, you get the same 80.6, which makes sense, right? But if I take them on an individual problem, the complex math problems scored a 76. That was like the very first topic we did. I would say probably what were some of the issues for people. In some cases, I know you used your calculator, but I don't think you knew exactly what you were doing. That was a few instances. In other cases, there's just either not reading the problem or just not understanding complex arithmetic still. So that led to some of the downfalls. Is there anything that anybody has a question on right now? Or, I mean, you're free to look at the solution. And I don't want to take a lot of time, but I'll take if there's questions. Maybe I should stop because no one seems to be necessarily looking really enthusiastic. Do you want me to go through the exam, or do you want to just cook on it yourself and come in and ask later? How many are interested in having me spend time going through some of the problems?
Number 6.
Okay, we'll get to it.
Oh, okay.
6 is a ways away, so. Okay, this second problem, what seemed to be, this one only scored a 68, so this was the biggest disappointment on the exam right here. Getting the period, not really a problem, 1 over the frequency. Getting the phase shift, I created the problem and I just sort of pulled some numbers out and I didn't even think hardly at all, and it came out as a unique kind of a solution. When you go through and plug in the t minus 2 and then multiply it out to get the argument that incorporates the phi now, so you have 2 pi times 1200t when you do the multiplication, and then you get 2 pi times 2400, or minus 2 pi times 2400. That's your value of phi, but I said it needed to be modulo 2 pi, and modulo 2 pi of that 2400 times 2 pi is just 0.
So you just divide by 2 pi.
Not really divide by 2 pi, just said how many 2 pi's are in 2400 times 2 pi. There's 2400 of them, so if you were doing mod 2 pi of that, you'd get back to 0 degrees. So it looks like we shifted it exactly by 2400 cycles. Is everybody following what I'm saying? The time delay of 2 seconds looked like an equivalent time shift of 2400 cycles, or 2400 periods. So it's kind of a silly answer, but it's still a valid answer. So when I looked at it, when I worked it out later, I said, this probably bothered some people, but that is what it is. It's exactly a mod 2 pi thing. Now maybe I could have made it more interesting by saying, instead of being 2 seconds, maybe it was 23 milliseconds or something along those lines. Then it would have been a little bit more interesting in terms of a fraction of a period, because we have 833 microseconds per period. But in terms of the angle, it works out as a mod 2 pi of 0. Okay, this problem right here, phasor addition, average on this problem was 87. almost everybody wrote the problem statement down correctly. In other words, they wrote down on their paper that this is what they had to do. A few people missed that minus pi over 2 factor from the sine shifting to a cosine. But almost everybody wrote down those 3 complex numbers, and then it was getting into it that there was a whole array of little errors here and there that crept in. Then, of course, there's also some of the more fundamental things that happen dealing with the arctangent, needing to get it in the right quadrant, but most everybody also seemed to track that just fine too if they were doing it pencil and paper. If you want to get your paper back, Nick, you got to come down here because I'm not going to pull myself off the microphone. Do you want to get your paper back? Okay, no comment. Okay, this next problem, the sketching problem, 95%. So I guess this one was plenty easy to do. It was a parabola and a linear line segment section. I just wanted you to have to go from a piecewise function to a sketch, and maybe later on the final you'll see the opposite of that. Just the idea of having descriptions of signals. Okay, in terms of this line spectra problem, this is kind of like something that was in the notes or in an example, or somewhere along the line we had something like this where we had, or in a homework problem where we had a DC term, and then we have the product of 2 cosines. And this would be like the case of the beat notes where you had a signal at 600 pi radians per second and another one at 650 pi radians per second. So when they multiply together, you get a sum and a difference. And this problem number 5 averaged an 81%, and I would say the overwhelming majority of errors in this problem had to do with, for whatever reason, and I don't know what it was, a very common error was to say, oh, this is at 300 hertz, and this is at 325 hertz. So the sinusoidal frequencies present in the signal are at 300 and 325. A lot of people just sort of blindly wrote that down, and I'm not sure what made you do that, because the 2 sine or cosine signals are multiplied together right there. The dot didn't stay in there, but it's cosine times cosine, so you don't have cosine plus cosine. If that would have been a plus sign in there, then that would have been true. If this would have been a plus sign in there, then there would have been spectral components at 300 and 325 at the positive and negative locations. But because it was the product, you had to multiply that out, which is the first thing I did. You got the sum and the difference. And so you got something at 1250 pi radians per second and 50 pi radians per second. And you then divide by 2 pi, so you've got 625 and 25 hertz. So the 25 hertz turns out to be the fundamental, and if you were going from 300 and 325, 25 hertz was still the fundamental, so a lot of you got that correct in either case. And then the 625 hertz is the 25th harmonic of 25, and of course the 25 hertz is the fundamental, or the first harmonic. Another common mistake was to, again, for whatever reason, maybe it's just moving too quickly, a lot of people had 6 in here for the amplitudes of the sinusoids. I don't know whether that's because you visualized it was 12 times the cosine, of one signal plus another, and then you just split it in half to get 6 on each side. Again, not realizing it was the product. But the trig identity brings in a factor of 1/2, and then you get the factor of 1/2 again when you split it between the positive and negative frequencies. Okay, so now we're on to problem number 6, which Jeff has a question on. Problem number 6 got an 80%. I gave a lot of partial credit on this problem, and admittedly it's not drawn perfectly to scale, and maybe that's what threw some of you off. But there's a triangle area up above and a triangle area down below. So you have to go 1/2 the base times the height to get that. If you look at the problem, I mean, that's the way I did it. First of all, I said, what's the period? The period is 6, and probably the way you'd look at that is, maybe this would be the better way of looking at it. That's one period right there. This is known as a sawtooth wave. It's just a sawtooth wave that's starting at -2 and going up to +10. So the period is 6. So the triangle that sits above has got a height of 10 and a base of 5. So that's this area. And then the triangle that sits below has got a height of 2 and a base of 1. So that's that area. Subtract them, and you end up with 24. The period is 6, so you end up with 4. I don't know, what bothered you?
It would be an area of the triangle. I didn't factor in the fact that some of it's below.
Okay.
And some of it's above.
Yeah, probably the most common error on this one, and again, it's been since last week that I graded these, so my brain is a little bit forgetting. I think a lot of people looked at this and they saw this is the 0 line in here. So you just found the area of the entire triangle as if it was sitting above 0 entirely. That was one of the common errors. There's a variety of errors, but they fell into basically 3 categories: done correctly, and then ignoring the baseline shift was probably the most common, but then there were at least one other common variation, maybe a couple other common variations. Okay, the aliasing or sampling theory problem averaged to 71%. And this one, for starters, something that an overwhelming number of people seemingly ignored was that I was looking for frequencies in hertz, not in radians per sample. So a lot of people just did that. So they gave me omega hat values rather than F in hertz. So when you plug into this, drawing the pictures, and even though the average on this problem was only 71%, which I would have liked to have seen higher, one of the things that I was really intrigued by was the fact that across the class people drew pictures in different ways. They drew the picture like I did here. They used the accordion picture with the thing that I handed out in that handout. Other people used just straight math calculations. So there was a good variety, which to me shows that everybody's brain, most of you have come up with a way that works for you and you're happy with it and you applied it. When I'm saying that, I'm saying the people that did these different things, they were successful. So everybody's found a technique that allows them to understand how to get the answer. So the 10,000 hertz is the sampling rate. So multiples of that are at 20K, 10K, our input signal's at 17. So we know we have to find which of the various multiples of the sampling rate 17K sits closest to, and it sits closest to 20K. So it's within the folding frequency, or 5 kilohertz, of 20 kilohertz when it's sitting at 17. So that's what we have to reference to in order to get the principal alias, and that ends up being 3 kilohertz. When you go to the second part of the problem where the sampling frequency was 6 kilohertz, you can repeat the same sketch that I did up above, but instead in my solution I just wrote it out using the math equation, which says that the principal alias has to lie less than fs over 2, which is 3 kilohertz, and then we have to find a value here, namely k, so that when we find the absolute value of the frequency that we're starting with minus k times the sampling rate, we have to get that value less than 3 kilohertz. And again, by trial and error, just looking at the math, you say, oh, it needs to be k of 3, and that puts me at 18, and 18 is 1 kilohertz away from 17. So that puts the principal alias at 1 kilohertz in that case. Again, if he would have drawn out the picture, it would have been the same kind of setup, except then we would have had multiples of the sampling rate would have been 6, 12, and 18, and then 17 is closest to 18, so that's the 1 kilohertz difference again. Any questions on this one? I tend to, in my line of work and in things that I do, these types of calculations are actually fairly common in just real-world scenarios, figuring out what's going on with aliasing and sampling rate calculations. So having a good ability to work these on the back of an envelope without having any math handbook or any complicated notes, these relationships should hopefully stay with you the more you have to use them in the future. Okay, the chirp problem is not unlike a chirp problem that was either in a homework or in the lab or maybe even in the worksheet, I can't remember. But we have a chirp that has an instantaneous frequency of 8,000 times t plus 1,000 hertz, and it's running for 1 second. So right from the get-go, it starts at 1,000 hertz, which some people did not quite get onto. And then it ramps up linearly from there, and it heads towards 9,000 hertz at 1 second. So this point here is going to 9 kilohertz, which most everybody managed to sketch that on their paper. At least that was fairly common. But the sampling rate's 10 kilohertz, so it folds at 5 kilohertz, or it aliases back again when it crosses through the boundary of 5 kilohertz. And so 9 kilohertz aliases back to 1 kilohertz because it's 1 kilohertz away from the sampling rate of 10 kilohertz. I did a little calculation down here, even though it was pretty simple in this case. I just wanted to know where it hits 5 kilohertz. So I just set up one equation and one unknown. I said, what value of t will I hit 5 kilohertz at? And half a second. I made the problem nice and symmetrical, but it wouldn't necessarily have to work out that way, right? So you can't always just seat of the pants draw a picture and say, I know exactly where it crosses at. You'd have to be really, I guess, good at drawing an accurate sketch, or your brain would have to work really fast. And it could have worked out at 0.125 or 0.125 or something. But it worked out very conveniently in this case. Okay, here's the filter and convolution problem. So we have a 3-tap FIR filter. So I gave you the block diagram in this case. You can see physically what the filter is doing. It's taking the present value and weighting it by 1, it's taking one value in the past and weighting it by -1, and it's weighting two values in the past by 2. So those are the filter taps, and they get plugged in right here as 1, -1, and 2. Then the sequence or signal starts at -1 and ends at +1. So we have to flip that signal over if we're going to use the table method as we went through in class. So this first value here is plugged in right here. Then the second value goes off to the left, and then the third value of 2 is 1 to the left of that. And that first alignment point is going to be when n is equal to -1, because that's when the signal flipped over and shifted to the right or to the left by 1 is going to align it with the k is equal to 0 point on h of k. Or another way of getting at that first alignment point would be this analysis in here, which says we're going to start at the sum of the two start values, which is the -1. We're going to end at the sum of the two end values, which is the +3. So when n is equal to -1, that has to be when the x of n minus k is sitting in there flipped around and aligning with one point in common, which is that first column right there. So then it's just a matter of stepping it through, marching the x of n minus k across, and getting the output. X of n minus k. A few people did this in a slightly different fashion. The average on this was 70. Most people, if they got off to a bad start, they had things misaligned in multiple locations. I don't know exactly what went through your heads if you got this wrong, but there were minor errors that people made, and then there were kind of like the major errors of almost everything being totally at random, which led me to believe you didn't know what you were doing, so you lost more points that way. This last problem was the highest percentage scored except for the piecewise signal. This was 88.6%. This was an interesting problem, though, where two wrongs gave the appearance of being right. And so when I graded the papers, I had to make note of the fact that you did come to the right conclusion, but for the wrong reason. And that was because two wrongs made the appearance of being right. You know what I'm saying? People will say two wrongs never make a right, but in math, two wrongs can make a right. The point is that the proof technique we had set up in the book and in the course notes was to say, let's delay our input through into the system by n naught samples. So that delayed input comes in right here, but this is part of the system, so it doesn't know what's going on. It's just like a clock tick, so the clock tick is n plus 2 out in front. So that's the output then with the delayed input, and then we delay the output for an input x of n, and that says we replace n everywhere by n minus n naught. So that gives the n minus n naught and the n minus n naught in those two locations, and now they obviously don't agree with each other because we effectively, this thing right out here is a time-varying coefficient. It's a time-varying gain. And I think a lot of you knew that, but proving that in math terms maybe was also another issue. I don't really know. I also see evidence when I grade papers of where people stop. In other words, a few of you were left in here at the end, and I had to shut the exam down, and I know that your brain is in the midst of thinking, but it's fading because it's the end of the period. So maybe that's what I saw for some of them. Any questions or comments you want to make? Well, if you go back in time from the start of the semester, does anybody want to start over again? Are you happy where we're at? And let's finish the semester. Because I'm thinking about that. I was upgrading papers late last night for one of my graduate classes. It's been a lot of work so far, and I definitely don't want to back up and play it again. I just want to keep going and get it to finish. Advising is next week, and I had a discussion with Aaron, I think, on Friday, right? I'll just reiterate something that he didn't realize, and I want to make sure everybody else in here does realize before you get signed up for advising. And that is 2205, which follows this class, is offered in the summer. Dr. Wong traditionally teaches it, and I think he's planning on teaching it again. And then 3205, which is the second semester of Circuits and Systems, is taught in the fall. 3205 is only taught once a year. It's only taught in the fall semester. 2610 is taught 2 times, and 2205 is taught 2 times a year. So everybody is got to funnel towards that one offering per year of 3205, which is next fall, which means for you guys, because you're taking 2610 now, it behooves you to not take 2205 in the summer and then be queued back up to be right on schedule with the rest of the junior class to take 3205 in the fall. If you don't take 2205 in the summer, then you're going to have to sit out a year, which has a major impact on most people's schedules. I'm not saying it to make you feel bad, it's just the way it is. If we were a large school, we'd probably offer all 3 of the classes every semester, but we don't do that. Anybody shocked by that? Okay, good. I want you to be on schedule because I want you to get out of here and get a job, because I think the economy seems to be doing somewhat better. At least EE jobs seem to be doing better, and the more years you spend in school not earning income, the less savings you have at the end of your career when you want to retire. Okay, chapter 6 is going into the fun topic of frequency response. And I gave you a brief preview of it 2 weeks ago. This week in the lab, you're going to get to play with this MATLAB GUI on frequency response. And this will be the lab where you're going to start designing some filters that you're going to use in lab number 9. So this is actually preliminary work is done in lab 8 on frequency response that moves into lab 9, and lab 9 is the last lab you're going to do. There's a team project, like I've said, but the last regular Friday lab is lab number 9. Each of them have 2 weeks, so it's still going to run almost to the end of the semester, but that's kind of where we're headed. So just to use this GUI for a moment, if this is the input sinusoidal sequence, and here we've built a digital filter, it's called an averaging filter, and there's a number of different types of filters that are selectable. It has 10 points in its moving average. This is the frequency response of the filter, and we're going to be studying that, this particular filter and frequency response in this chapter. The red dots indicate that I'm putting in a normalized digital frequency of 2 pi times 0.05 radians per sample. The signal that comes out of the filter is the magenta. And if I was to move the frequency of the input signal, say to 0.1, now it sits right at one of the nulls of the frequency response, so nothing gets through at that particular frequency. And that's one of the things I alluded to 2 weeks ago. And that's one of the things that we kind of started seeing actually at the very beginning of the semester. It's one of the opening slides I talked about a filter that can, I think I talked about it, maybe I'm thinking back to another occasion, but at any rate, when we were talking about waves bouncing around in a room, I know we talked about the idea that when you hear a signal at a certain point in space, you've got a superposition of waves that travel different distances, so you get to have constructive and destructive interference. A digital filter performs that operation all within the FIR structure, and it can do that too. So effectively, we see where the frequency response is nulling down to a magnitude or gain of 0. That's a particular behavior of the filter and the design of the filter. We don't always just want to remove certain signals. We might want to just attenuate a whole band of frequencies, but many filters have the properties that they're going to have certain frequencies that totally annihilate the input signal. So how do we get at frequency response? Mathematically, it ends up being something called the Fourier transform. However, in this book, we're going to kind of keep it, the Fourier transform, formally at a low level and not use that terminology, just use a definition that amounts to being the same as the Fourier transform, but not go deep into it at this time. So we'll start by assuming we have a complex sinusoidal signal, e to the j omega naught hat n. Remember, the omega naught hats was the book's notation of saying if we started off with an analog signal, 2 pi f naught, and we were sampling it at fs samples per second, that's how we come up with this normalized digital frequency in radians per sample. So if we suppose that the input has actually got a complex amplitude of a e to the j phi, and then it's got the rotating phasor part of e to the j omega naught n, what happens when we drive that into an n+1 tap FIR filter? So this is the equation for the FIR filter's output from the input and the filter coefficients. That's basically our convolution sum equation. If we plug in the special case of the complex sinusoid, and this is even more specialized than in the past because we're assuming that the sinusoid has been up since the beginning of time, a very long time, mathematically since the beginning, and goes on to infinity. So it's a sinusoid that's present for all time. We can plug that into our convolution sum equation 6.2, and drop that input in right down in here and replace n everywhere by n minus k, and then a very nice result comes out of this. Namely, we can factor out the terms not involving k, void of k. That sounds weird, thinking of a function that returns void in C, right? That's not what I'm talking about, but where terms that don't have k in them can move out in front of the sum, and the terms that involve k stay inside. So what we're left with then is a complex coefficient weight, which was namely the input. So that was the input, and that was the input rotating phasor. So we're getting out exactly what we put into the filter, except that we're now multiplying times this weight. So the net impact of the filter on that complex sinusoid is to just apply a complex weight, which when I say a weight, I mean it has a magnitude and it has an angle associated with it. And that's going to vary depending upon what the frequency is of the sinusoid, because it's actually a function of omega naught hat. Or in general, for an arbitrary omega hat, This is what we call the frequency response. So we have to sum up the filter coefficients with e to the minus j omega hat k, and then we're going to get a function of omega hat when we get done with that. Formally, this is called the discrete time Fourier transform, but like I was saying in the opening of the chapter, we don't really bring that up to the forefront because we're not wanting to get you all concerned about all the details of the Fourier transform. You'll study it more later in the 2205 and 3205. And if you take some other courses in signals and systems, you'll definitely see it. When I teach modern DSP in the fall, we start off with the Fourier transform in the first couple of weeks of class. But just understanding that this is the frequency response, in other words, the response of the filter to a sinusoidal signal that's been applied back at minus infinity. We'll explore more why that minus infinity is in here. It's not super rigorous that it has to start at minus infinity. We just need to have it start early enough in time so that the output is in what's called steady state. And we'll be exploring a little bit of the transient response in this chapter too. The basic idea is that when you apply a sinusoidal signal to a linear time invariant system, you're guaranteed of getting out a sinusoidal signal. Now maybe it has an amplitude of 0 because the filter annihilates it, but you still have a sinusoidal signal that comes out for a sinusoid that goes in, and that's true of an electronic circuit as well. When you start studying circuits in 2205, this will be the property of a circuit composed of linear elements like inductors, capacitors, resistors, and so on. The notation that's used here is h of e to the j omega hat. Rather than just saying it's a function of just omega hat, the emphasis on the e to the j omega hat is really for two reasons. It's going to allow us to be consistent with the z transform that's defined in chapter 7, and it also emphasizes the fact that the frequency response is periodic, and we'll explore that more a little bit later in this chapter. So by having it as an e to the j something, we know that it's got a periodicity associated with it because e to the j is a mod 2 pi function, right? So right now, for the case of a complex sinusoid driving into a system, we're seeing that the output is just that input times this h of e to the j omega naught hat. Now this only holds true for a complex sinusoid starting some point back in time in the limit minus infinity. This result does not hold for general signals, though. For a general signal, we still have the property, and the only way we can generally say for an LTI system is that y of n is x of n convolved with the impulse response. But for the case of a complex sinusoid, we can also get it in terms of the frequency response times the input. And there's going to be a connection in there, and actually that gets developed further over the next couple of chapters. It actually ends up being a property of Fourier transforms and then of Z transforms. It's called the convolution theorem, and that will get developed as time goes on throughout the rest of the semester. So what is particular about the frequency response? Well, it's a complex quantity, and it's a function of the frequency variable omega hat. So in general, we're interested in having it in polar form. And if we do it in polar form, then we have the magnitude. This piece is the magnitude. And then we have the phase sitting up over here. Most of the time, we're more interested in the magnitude response, but phase response is obviously important in some applications. But magnitude response is what really lets us know what the filter is filtering, because if the magnitude response goes to 0, that tells us the filter doesn't let any signals at those frequencies get through. And that's probably the first and foremost thing. if the magnitude response has got, say, a value that hovers around 1 over some range of frequencies, then that tells us those are the frequencies that pass through, and anything else gets blocked. And that's one of the challenges that you'll be working on in Lab 9, because what you're headed towards making is a touch tone dialer and then a touch tone decoder, all in with digital filters. So what's a touch tone encoder or dialer? Is going to be some software that you give it a string of digits, like a 7-digit phone number, and it will produce the touch tone series of frequencies. What is the touch tone? Well, when I press a button on the phone up here, according to the standards body that came up with this, when I press one button on here, I'm getting a row frequency and a column frequency. So when you dial on a telephone keypad, you hear 2 sinusoidal tones whenever you press a button. You get a row and a column. If you want to be able to decode that, it's called DTMF. Digital multi-tone signaling. So when you want to decode that, you have to be able to figure out which 2 tones are present. And you're going to be designing a bank of bandpass filters that will decode signals for the row frequencies and the column frequencies, so then you can decode the analog tones that you're listening to back into the telephone number that was or button that was actually pressed. That's kind of the capstone project that you do in the lab. That's in Lab 9, where you actually start building that out. It's a lot of fun, actually. And it's a culmination of everything that's gone on throughout the semester. It also ups the ante on the software coding side of things, too. You have to write more modules of code for that than in anything else you've done so far. So what's one really neat interpretation about the frequency response is, we just think of the magnitude response, we see that if we apply the complex sinusoid to the system that has magnitude and phase given here, the magnitude response, which is the A, will now sit out in front as A times the magnitude of h of e to the j omega hat. So the amplitude at the output is directly modified by whatever the amplitude response is of the filter. So if the filter has a high gain, it blasts that particular tone through. If it has a gain of 0, it totally annihilates it. The angle rotates the phase. And rotating the phase on a single sinusoid is not maybe all that devastating, because if we're just listening to a single tone, our brains don't really make out whether it's at 0 degrees, 180, or 45 degrees. We can't really make anything out. But if you put multiple sinusoids up at different frequencies, suppose they form a chord sound on a piano, and you rotate the phases of them differently, now you're talking a difference, because that's what makes up a particular sound. It gives it its timbre or color. You know, if the different harmonics are at different phases, that gives it a different coloration than if they're all at 0 degrees, let's say. So let's take a simple example of some of the manipulation that goes on here. Suppose we have a filter that has these 5 coefficients, 1, 1, 3, 1, 1. So this would be an FIR filter. I don't think I have it pictured on the next page. So those are the coefficients to the filter. Go in and find the frequency response. We just plug into this formula right here. We put the BKs out in front of the e to the j omega hat k's, complex factors, and out pops this sum of complex numbers. We need to evaluate then at each value of omega to get the composite frequency response. And mathematically, we can leave it just as is, and MATLAB or Mathematica would have no problems dealing with it. If you want to get fancy and do some manipulation, which is frequently done to get more of a flavor for what the filter actually is doing to both the magnitude and the phase, one of the common games to play is to factor out some e to the minus j omega factor out in front. So in this case, the factoring that's done is to factor out this central value. That's the center value of the filter. Factor out that e to the minus j2 omega, and then in order to keep everything intact inside the square brackets here, we've had to put in some e to the plus j's and some more e to the minus j's, and then the center value is just now a 3 all by itself. So the value in doing this is to get more of a flavor for what is going on in the magnitude and phase response, and in this case, you're thinking Euler's identity should say these two guys are now poised to form a cosine, right? And these guys are poised to form a cosine. And then the center term stands alone. So that's how come in this next line down here I've got the 2 cosine 2 omega hat. That's from the outer two complex exponentials. And then the 2 comes from the Euler's identity denominator. And flipped up to the numerator because you've got to scale it off to make it into a cosine, and then the middle two e to the j's just become a cosine, form up a cosine omega hat. Again, I want to emphasize that you don't have to do this, but it gives you an added insight on some occasions, and you'll see that in some of the workings in the book, other examples in the notes, and some of the homework problems. And there is a new homework sheet up there right now, which I tentatively want to have turned in by Friday, but we can negotiate on that on Wednesday. I do want to have a quiz on frequency response on Friday, though, and it's really important to get up to speed on this. I know we've come off a spring break, but you should be ready to just crank up the volume to full blast and say, we're going to just cook through the rest of the semester and get this done. So the sooner we can crank it up, the sooner we can be up and rolling at full speed again and just, get things done. So the magnitude response is just as given there, and then the phase is just what's due to this term right up in here. That's the only complex part of the expression now that's left, so that's a minus 2 omega hat is the angle on this filter. And I put the blank in here just so you could go in and do some more of the math on this if you want to. If you're wondering how I could be bold enough to say that, it has to do with the fact that the way that 2 cosine and the 2 cosine of 2 omega come together, the most that could happen from this term right here is, this is real, but it could be negative. In this particular case, that doesn't happen, but if it did, then we'd have to modify, you have to put in some plus or minus pi factors in here if that was to ever happen. In other words, that 3 plus 2 cosine plus 2 cosine, if it was ever to go negative, that would say we had a 180 degrees phase shift, and that would show up in the angle. But like I said, in this case, that doesn't happen. MATLAB can plot this out by just taking that form that we just had and putting it in directly and setting up an omega vector that runs from 0 to 2 pi, and then do the plotting using the absolute value of the complex quantity h to get the magnitude response, and then to plot the angle, just use MATLAB's angle function. I've got it shown on the next page of the notes, but just to let you know that you don't have to even be that formal about it. You could just, by the way, when you run this DLTI demo for the lab on Friday, don't be surprised if you get some error messages from the MATLAB environment, because there's some compatibility issues. It's just giving out warnings, though. It's not crashing the system. It's just giving out warnings. So that's what happened when I started it earlier today. But suppose I wanted to just do that frequency response without doing the trig and Euler identity factoring. I could just go omega goes from 2 times pi over, let's do 500 points, to 2 times pi. And then if I wanted to get my frequency response vector, I could just go back to what I have in the notes here and just say, I could just start from this guy right here. Just do it entirely from that. So it's 1, 1, 3, 1, 1 with the e to the minus j's thrown in there. So back in MATLAB, what I would do is I would just do 1 times exp of minus j times 1 times w. And the next one is a 1, except I have to have a 2 in there. And then this one I have to have a 3 out in front and a 3 on the inside. And then I have to have a 4. 0, 1, 2, 3, 4, 5, yeah, 4. And that's my 5 taps, right? 1, 1, 3. Yeah, I'm missing the 0. This one needs to have the 3 on it, though. 3 needs to go there, and that needs to be the 1. So I've got e to the j 0, e to the minus j 1, e to the minus j 2, 3, and 4. Put a semicolon on there. And now I could just go up and do my plotting with the ABS of H. That's the magnitude response. Then if I wanted to plot the angle, I could plot that on top of there, or do a subplot on there. I think I have that over here in the notes, though, so I really don't need to do that again. So I just did a subplot here. So there's the magnitude response up above. And see, it never does touch 0, so it never goes negative. And there's the phase shift. And this is just a constant phase slope down of minus 2 omega. And what MATLAB is doing, when it gets to minus pi, it wraps it by adding 2 pi onto it. So it wraps it so it comes back up and does that again. That's just a mod 2 pi plotting property that MATLAB has. Make sense for complex numbers? Now, if you're wondering about that, I'll just show you something that sort of an interest item for MATLAB. So let's plot that angle. Okay, so MATLAB automatically wraps it. But I said the phase was minus 2 omega. Well, MATLAB has a way of dealing with that, and it's called the onwrap function. The onwrap function will take the phase, and rather than modulo 2 pi wrapping it, it will unwrap it. So you can do that too. Or if I did a hold on that, took the straight wrapped angle, there's the difference. In a lot of applications that I deal with, the unwrapped version is what I'm more interested in. If you study complex variables, then that might be more of an interest to you too. How many times does it encircle the origin or something like that with the phase angle? So the next thing, the little red marks on here, is the last thing we'll talk about. Suppose the input is coming in at 1 radian per second. So we put a complex sinusoid in at 1 radian per second, and it's at an amplitude of 5 and a phase of 0. So that says we just apply that input to our filter's frequency response. And this is the frequency response right here. This is h of e to the j omega hat at omega hat equals 1. Plug that in there, set the frequency at 1 radian per sample. The input gets butted up against the end of it here. And the output comes flying out as a complex sinusoid at the same frequency, e to the jn, but now it has a phase shift of e to the minus j2 and an amplitude of 16. Is that what I would expect? Well, we can go look at this and say, what is the filter doing at 1 radian per second, or 1 radian per sample, and that's this guy here. We can pick off our plot and see that the phase shift is minus 2 radians, and the amplitude is exactly 3.248. So does that make sense? The output sinusoid is going to be shifted by 2 radians, and the amplitude of the sinusoid came in at 5. So it came in at 5, and this now comes out at 5 times the amplitude gain provided by the filter, which is the 3.248. And if you multiply those two numbers together, you find out that is indeed the 16.24. So it's like that signal got that gain applied to the filter, and we can see that the filter's got different gains at different frequencies. It's not just unity, it's not 5 or 6. It takes on all different amplitudes depending upon what frequency we're at. Does that make sense? This is a fundamental concept of this chapter. A sinusoid goes into a system, it picks up the magnitude response of the system at that frequency and the phase shift response at that frequency. So in this particular case, this sinusoid at 1 radian per sample is picking up a gain of 3.248 and a phase of minus 2. And we see that in this expression here for the output. The amplitude goes from 5 up to 16.24, and the phase shift, which at the input was the 0 in here, is now the minus 2. And that's what the system has done to the signal. All of us know that filters really, really work. I mean, not just from this class. You listen to signals through different filters in your stereo system. You've got the treble and the bass controls, and that shapes the sound. A lot of you probably like to listen to the bass turn way up, right? So you crank the bass knob all the way up to get that shuddering sound so that you're the car on the street that everybody wonders what's going on because the car is shaking and vibrating. So what does that mean? You must have made the low frequencies get lots of gain so they're really strong and powerful. And that's what's going on here. Actually, in this particular example, it looks like the low frequencies are getting the most gain, like a gain of over 7 down at close to DC. That's what's going on right in here. We'll pick up with this more next time. Superposition holds, and that will be nice. We're going to get a really fundamental result, which this page right here, 6-7, I will be talking about this over and over again, and people will come to see me in my office, I predict, and I'll keep saying, look at this equation. This is a really important result for the rest of the semester.